Alright, so it's my pleasure to introduce our next speaker. Actually, before I do, the supervisor, Stephanie van Willigenburg, who could not be here, has asked me to do this on her behalf, because Vasu is nearly finished with his PhD and he is apparently tops. So, as I'm sure you'll find out from his talk, about the nil-hacker modules for quasi-symmetric Schur functions.
Thank you for the introduction. Let me also thank the organizers for giving me this opportunity to talk. I'll be talking about zero-hacker modules for quasi-symmetric Schur functions. And this is joint work with Steph van Willigenburg. Here's the outline of the talk. I'll start by introducing the algebra of quasi-symmetric functions, denoted QSym. I'll talk about our main combinatorial object called Standard Reverse Composition Tableau, abbreviated SRCT, and I'll use those to introduce quasi-symmetric Schur functions. I'll give you a brief overview of zero-hacker algebra and the associated representation theory. Finally, I'll give a zero-hacker action on SRCTs and use it to give you some results on quasi-symmetric Schur functions. But first, some preliminaries. So, composition of a positive integer n is a finite ordered list, in this case alpha 1 up to alpha k, whose sum is n. So 2, 2, 1, 3 is a composition of 8, as 2 plus 2 plus 1 plus 3 is 8. And recall also this folkloric bijection, taking a composition with k paths, alpha 1 till alpha k, to a subset S with k minus 1 paths, and you basically take a composition of n to a subset of the first n minus 1 positive integers. And the way you do it is you take the first k minus 1 partial sums. So if you look at this example here, the 2 on the left gives you, the first partial sum is just 2. So that gives you this 2. The 2 plus 2 gives you this 4. And the 2 plus 2 plus 1, these 3, give you the 5. And it's clear that this bijection is reversible. You take consecutive differences going in the opposite direction. So if I start with this composition alpha, I'm going to call the associated set alpha, and going back in the opposite direction, if I start with the set S on the right hand side, and I get the associated composition as comp S. So QSym is going to be the algebra of quasi-symmetric functions. It's a graded algebra. The degree gives the grading. And I'm going to consider the nth degree graded piece, QSym superscript n. It's going to be the Q span of these functions f indexed by compositions of alpha. And the way you define these f's is, you take monomials xi1, xi2 all the way till xin with this condition: i1 is less than or equal to i2 is less than all the way up till in. And furthermore, if j belongs to set alpha, then ij is strictly less than ij plus 1. So if you sum over all such monomials, you get the fundamental quasi-symmetric functions, also called the Gessel quasi-symmetric functions. So here's an example of f12. The set alpha in this case is just the singleton set containing 1. So you're going to be summing over all monomials xi1, xi2, xi3, where i1 is strictly less than i2, and i2 is less than or equal to i3. So the less than or equal to gives you x1, x2 squared and so on. The all strictly decreasing ones or increasing ones give you x1, x2, x3 and so on. Okay, so I'm going to associate this diagram with any composition alpha, and the way I do it is I take this left justified array of boxes with alpha I boxes in row I from the top. So this is the composition diagram for 4, 2, 3. So it's got 4 boxes in the top row, 2 in the middle and 3 in the third row. Now we've got boxes and we're going to fill them with numbers. So standard reverse composition tableau, tau, of shape alpha is a filling of the diagram I showed before with positive integers from 1 to n. Okay, so distinct positive integers. And with these 3 conditions, the rows are going to strictly decrease from left to right. The first column, only the first column, strictly increases from top to bottom. And then this crucial condition here, it's called the triple condition. If you're looking at any configuration of this type, the B and C in the same column, and A lying adjacent to the B, then if A is greater than C, then B must be greater than or equal to C. So you can check these three conditions here in this example. It can be checked quickly that the rows are indeed strictly decreasing from left to right. That should be weakly decreasing, but for standard, oh yeah, okay. In the case your standard coefficient tableau, it is strictly decreasing. Okay, yeah, all good. So the rows are indeed strictly decreasing from left to right. The first column is 2, 8, 9, 10, strictly increasing from top to bottom. And here's the first triple of the said form. So the 8 is greater than the 5, so it better be that the guy sitting next to 8 is also greater than the 5, and indeed 7 is. And there's one more such triple here. The 7 is greater than the 4, and so is 6. Okay, so now we do in a tableau, we can associate a descent set. So if you have tau of size n, then I'm going to associate a set of descents called des tau. And the way I do it is I consider all I in the filling such that I plus 1 appears weakly right of I in tau. This is clearly a subset of the first n minus 1 positive integers, and you can use the bijection I had mentioned before to associate the corresponding descent composition, and I'm going to call it comp tau. So in this example here, you see that the descent set is 2, 5, 8, 9. So here's the 2, 3 is weakly right of the 2. Here's 5, 6 is weakly right of the 6 is weakly right of the 5. The 8 and 9 are in the same column, so 8 is in the descent set, and the 9 and 10 are in the same column, and 9 is in the descent set. So the descent set is 2, 5, 8, 9, and the associated composition is 2, 3, 3, 1, 1. Okay, so we have descent sets, descent composition. So the next slide will introduce the quasisymmetric Schur functions. So this quasisymmetric Schur function, calligraphic S indexed by alpha. The way you create it is, you consider all SRCTs of shape alpha, you take the descent compositions, and you take the F indexed by that descent composition, and you sum over all these Fs. What you get is the quasisymmetric Schur function indexed by alpha. Okay, so here's the first theorem. This is proved by Hagelin, Lioto, Mason, and Van Wilkenburg. The nth degree graded piece of Q sim is spanned by these functions when alpha ranges over all compositions of n. And here's the cool property. If you take a Schur function indexed by partition lambda, then it actually is the sum of all Quasi-Schur functions indexed by all rearrangements of lambda. So this alpha twiddle is just denoting that if you sort a composition alpha, you get the partition lambda. And there's some other properties it has, some Schur-like properties. But before that, we should get this example. So I'm going to calculate this Quasi-Schur indexed by the composition 2, 2. Here are the two composition tableau of shape 2, 2. The first one has descent set just 2, and this gives you the F2, 2 term. And the second one has descents in position 1 and 3, and that gives you the F1, 2, 1 term. Okay. So here's some property. The F expansion of the Quasi-Schur should remind you of the expansion of the skew Quasi-Schurs as also like F and descent sets. There's a notion of quasisymmetric Koska numbers once you expand Quasi-Schur in monomial quasisymmetric function spaces. There's also Peary rules if you multiply by the F indexed by a row. And there is such thing as a skew Quasi-Schur, which you expand it, you get a quasisymmetric Littlewood-Richardson rule. So this I'm not in any way saying this is the only Schur-like basis. This is a very coolly named dual immaculate basis. But we're not going to deal with that one here. Okay, so my aim is to give some representation theoretic context to the quasisymmetric Schur functions. And I'll start by talking about the zero-Hecke algebra. So this is the C algebra generated by some indeterminates T1 to Tn minus 1 modulo these relations. The first one says that the Ti's are idempotent, so the squares themselves. The second one is just the braid relation. And the third one says that Ti and Tj commute if I and j are far apart. So if I and j, the difference is greater than or equal to 2, then Ti and Tj commute. Okay, the representation theory of the zero-Hecke algebra was studied by Norton in 1979, and she proved that this 2 to the n minus 1, one-dimensional mutually non-isomorphic, irreducible representations of Hn0 and they're naturally indexed by compositions of n. And I'm going to call the irreducible representation indexed by some composition alpha by this boldface f underscore alpha. And the work of Duchamp, Probe, Leclerc, Thibon allows one to associate a quasisymmetric function with any zero-Hecke module. And this function, it's called the quasisymmetric characteristic, and it's denoted by CH. And for this irreducible representation up here, the map CH basically takes that module to the fundamental quasisymmetric function indexed by alpha. So the CH is actually a map on the Grothendieck group, but let's just gloss over that fact. Okay, so before I find a module whose characteristic is the Quasisymmetric Schur, we need this notion of attacking descents. So if we're given a SRCT tau for some composition alpha and a positive integer I, then I call I and I plus 1 attacking if either they belong to the same column in tau, or I and I plus 1 are in adjacent columns, but I plus 1 is positioned strictly southeast of I. So these are the two conditions which decide whether I and I plus 1 are attacking. So if you look at this example, the 2 and 3 are attacking because they belong to adjacent columns and 3 is southeast of the 2. And for the same reason, the 7 and 8 are attacking. The 9 and 10 are in the same column. So 9 is an attacking descent, and 10 and 11 are in adjacent columns with the 11 southeast of the 10. So 2, 7, 9 and 10 are attacking descents. So I'm going to use this notion to give an action on Tableau. So given a SRCT tau and a positive integer I, I'm going to denote by Si of tau the filling obtained by interchanging the positions of I and I plus 1. Okay, so here's this action. So I'm going to define operators pi I, and the way I'm defining them is, you take a SRCT tau, pi I of tau is itself if I does not belong to the descent set. If I and I plus 1 are attacking, then you kill this SRCT. And if they're non-attacking, then I'm going to interchange the positions of the I and I plus 1. So yeah, basically attacking, you kill, non-attacking, you do some change. So here's an example. So here's the tableau under consideration. So you have 2, 7, 9 and 10 being the attacking descents. You have 1 and 5 being the non-attacking descents. So if I does not belong to the descent set, which are these guys, 3, 4, 6, 8 and 11, the tableau is fixed by pi I. If I is 2, 7, 9 or 10, and these are attacking descents, then you map the tableau to 0. And in the other two cases, you basically switch the position of the 1 and the 2 from here. So the 1 is now in the first row. And pi 5 of tau, you switch the position of the 5 and the 6. So any questions regarding the action of pi i's?
If the descent is non-attacking, you swap them, you just get a...
Yeah, you get a valid SRCT of the same shape. Yeah. So, yeah.
Excuse me, maybe I missed something. Why 5 is not attacking?
So I said the attacking condition is you got to be in adjacent columns. So I and I plus 1 in adjacent columns.
Okay.
So those two are far apart. Okay, so here's what we proved. The pi I squared is pi I. The pi I satisfy the braid relations, and they commute if the absolute value of the difference between I and j is greater than or equal to 2. So this should look familiar. And you see that they are the same relations as the defining relations of the zero-Hecke algebra. And hence, we are in shape to construct some modules of the sort we desire. Okay, so S alpha is going to be this C-linear span of all SRCTs of shape alpha. So here's the first theorem. S alpha is the zero-Hecke module whose quasisymmetric characteristic is the Quasisymmetric Schur indexed by alpha. So this one follows from standard techniques. You construct a filtration where individual, like the quotients, give you the right Fs. So once you have such a module, you can ask questions about its structure, like indecomposability and cyclicity. So I should mention that this talk would have ended here had I not met Vic Reiner last June, and he gave me way too many questions. So the rest of the talk is answering some of them. Okay. So I'm going to talk about cyclicity and indecomposability, and for that we need this notion of a simple composition. So I'm going to call a composition alpha 1 till alpha s simple if it satisfies this condition. If alpha I is greater than alpha j, and both of them are greater than 2, and alpha I precedes alpha j, so this is I less than j, then there should be some index k between the two of them, such that alpha k is 1 less than alpha j. So slightly involved, but okay. So here's the 4 and the 2. The 4 precedes the 2 and is greater than the 2. So if this composition is to be simple, there should be a part of length 1, which is 1 less than 2, between them, and there it is. And here's the 5 and the 3, and since this composition is simple, there should be a part of length 2, which is right here, and you can see that 5 and 2 you compare, then there's a part of length 1. So this is indeed a simple composition, and this guy is not, because you can look at the 4 and the 2, and there is no part of length 1 less than the 2 between them. And similarly with the Alright. So here's the theorem. S alpha is cyclically generated by a single composition tableau if and only if alpha is a simple composition. So I should remark here that I don't have a characterization for all cyclic S alphas. These are the special ones which are generated by one tableau. You can have some modules which are like generated by some very ad hoc looking linear combinations. And it so happens that if you're a simple composition, then you're also indecomposable as an HN0 module. So simple composition basically decide your indecomposability. And the proof involves looking at this certain special submodule that we're calling the canonical submodule. And don't look at the definition here, the example is much easier to follow. I'll define something called the canonical tableau. So if I'm looking at the composition 3423, the canonical tableau with this composition shape is going to be a filling of the first 12 natural numbers from 1 to 12. And the way you do it is you start from the top row and fill the numbers 1 to 12 in that order from right to left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 11, 10. And you do this for any composition shape alpha, you get something which is called the canonical tableau of shape alpha. So I'm going to look at the linear span. Okay, So E alpha is a set of all composition tableau where every column is increasing from top to bottom. So it's not just the first column. Now we are imposing the condition that every column increases from top to bottom. And S alpha is going to be the C linear span of all SRCTs that belong to E alpha. So it turns out that this S alpha, alpha comma E alpha, is also a cyclic module, and this one's generated by the canonical tableau. So this one belongs to every submodule that I talked about earlier. And this is the one which basically decides the indecomposability and cyclicity. So it's worth looking at its quasisymmetric characteristic, which I'm going to denote by C alpha. And it turns out they also give you a basis for the nth degree graded piece of the quasisymmetric functions. And furthermore, they're a particularly nice set. They're mutually non-isomorphic and indecomposable. So these are 2 to the n-1 mutually non-isomorphic indecomposable HN0 modules. Yeah.
The same, the reproducible index are the same alpha.
Yes.
Can you repeat the question?
So the question was, are the top the same as the irreducible indexed by the composition alpha? So you've got this F expansion, and you look at the leading term, and one of the F alphas appears when I write these guys in the F basis. Okay, So I'm going to define this partial order on composition tableau of shape alpha. And let's just look at this example because that will make things clear. If I have tableau tau 1 and tau 2, I say tau 1 is less than tau 2. If I can apply a sequence of these flips and go from tau 1 to tau 2. So this tableau here is less than this tableau because I can switch the 1 and the 2 and reach the guy on the right. So this is the partial order I'm considering on SRCT alpha. Okay, so with this partial order, the set of all SRCTs whose columns are all increasing from top to bottom is isomorphic to a subinterval under the Weak-Bruha order on Sn. It's the left Weak-Bruha order. So we have been flipping i's and I plus 1, so it's not very surprising that there is something to do with the Weak-Bruha order. But there is some work which goes into showing that this has a unique, the poset has a unique top and a unique bottom element. So yeah, you basically get a lattice because of the Weak-Bruha order on Sn property. Okay, so now I'll describe some dimensions of some of these modules, the canonical ones. Okay, I'm going to call a composition alpha a strict reverse partition if the parts are increasing, if alpha 1 is strictly less than alpha 2 and so on. And its shifted reverse diagram is going to be this diagonally justified array of boxes with alpha I boxes in row I from the top. So here's the reverse diagram for 2, 4, 5, the shifted one. And again, I'm going to deal with fillings. So fillings will basically look like the shifted Young tableau. We're going to use reverse alphabet. So given a strict reverse partition, a shifted reverse tableau is a filling with positive integers from 1 to n. And you impose these two conditions here. The columns increase from top to bottom. So you look at this example here. All the columns are indeed increasing from top to bottom. And the rows decrease from left to right. So the rows are 11, 10, 9, 7, 4, 8, 6, 5, 3, 2 and 1. So they're indeed increasing from left to right. Here's the first theorem. If alpha is a strict reverse partition, then the dimension of the canonical module indexed by alpha is the number of shifted reverse tableau of shape alpha. These guys have a shifted hook length formula, so you actually do have a closed form in the case alpha is a strict reverse partition. And here's the proof. So you start with some element in SRCT alpha, all of whose columns are all increasing from top to bottom. And what I do is, I do this sliding. So I leave the bottom row fixed. I slide this guy 1 unit to the right, and I slide this top guy 2 units to the right, so as to get a diagonally justified array of boxes. And the triple rule property ensures that what I get is a genuine shifted reverse tableau. And you can easily see that this is reversible. You make stuff from diagonally justified to left justified. And this establishes that there's this canonical submodule with this dimension. And I'll draw this link with truncated shifted reverse tableau. So given strict reverse partitions alpha and beta, the truncated diagram, alpha skew beta, is what you would obtain if you had the shifted reverse diagram of alpha and you removed the boxes corresponding to beta from the bottom right. So if 2, 4, 5 is alpha and 1, 2 is beta, then I'm going to remove these boxes with the red dots. And I get this, and this is the truncated shifted reverse shape corresponding to 2, 4, 5, skew 1, 2. So we can talk about fillings of these guys. So the same conditions that you use for the shifted reverse tableau, you can impose them here. So the columns increase from top to bottom, while the rows decrease from left to right. And here's an example of a truncated shifted reverse tableau of shape 2, 4, 5, skew 1, 2. So, okay. So if you're looking at rectangular shapes, so these are the n to the k denotes parts of length and k of them. You can map them again using the same bijection that I showed earlier, the sliding algorithm. you can map them to a set of truncated shifted reverse tableaus of a certain shape. And these ones are actually a partial staircase skewed out by a full staircase. And the proof is absolutely similar to the one I pointed out earlier. And in the case you're restricting yourselves to rows of length 3 and k of them, you actually get a nice closed form. There's 2 to the k minus 1 such tableau. And you actually get that this poset here with the partial order I mentioned earlier is actually isomorphic to the Boolean lattice of subsets. Okay, the final result. So yeah, so if you're looking at this composition alpha of all the way up till n with part equaling n repeating, then E alpha, which is the dimension of the canonical submodule indexed by alpha, is the number of truncated shifted reverse tableaus of staircase minus a box. And if you are the sort who likes to have a closed form for things, you leave it to other mathematicians to do it. The right hand side is already being computed in a different context by Canova and independently by Adin, King and Reutemann. Okay, sorry. Yeah. So here's this beautiful formula here. So the G's are the number of shifted reverse tableaus of staircase shape, and you've got this product and quotient involving the Catalan numbers. And these are some final questions. So the easy question, I haven't managed to solve it yet, so probably. So how many simple compositions are there? So which would tell you how many indecomposable modules in HN0 are there. So when is this poset corresponding to the canonical submodule rank symmetric? From all the data I've looked at, it is definitely rank unimodal, and I've looked at compositions of size 12. Not always rank symmetric. You could talk about the basis, you could talk about the properties this new basis of quasisymmetric functions possesses. Finally, you could ask for closed forms for other truncated shifted reverse tableau. And finally, here's this one. If you look at this generating function, so I'm looking at canonical tableau with shape n to the k, then this generating function seems to be rational, and furthermore, the sequence actually satisfies a linear recurrence with integer coefficients. The case n equals 4, the case n equals 3 I already showed is 2 to the k minus 1. The case n equals 4, OEIS tells me it's present in Joel Lewis's thesis, who attributes it to Greta Panova, the enumeration. So, okay, that's all.